All right, we're going to review Unit 1 of AP Physics C, Kinematics, for the AP Physics C test. That's in about like a month and a half at this point. So the deal with kinematics is that it's basically applied math, right? I always hate when people say, oh, physics is just applied math, because I believe physics is way more than that. It's about observing nature. It's about understanding why the world works the way that it does. But when it comes to kinematics, yeah, it's really just modeling motion and using math and graphs to kind of predict how motion or how like objects move. And an example would be something in free fall. If I take like an apple, right? You know, kinematics isn't really concerned with how this or why this apple falls. What kinematics is concerned with is how can we like predict its motion, right? Because we know that in this world there's gravity, and this gravity is accelerating us. So kind of the first, I guess, big idea is that acceleration is the change in velocity, right? So if you have an object in free fall, it's fine. So its velocity at any point, like its final velocity after a certain amount of time, is going to equal whatever its initial velocity is minus g times time. So a couple things, right? You got to choose which way your direction is, right? So if I can say that up is positive, and in that case, there's going to be a negative acceleration, right? And that just means an acceleration pointed downwards, right? These are all vectors. We're dealing with velocity that has a direction. We're dealing with acceleration that has direction. And I guess in this case, right, initial velocity depends whether you throw it up or down. And another thing to note is that, well, on Earth, G just represents the gravitational field, or it really, in a kinematic sense, it really represents the acceleration due to gravity, which ends up being 9.8 meters per second squared. So, let's just say, just for, actually, yeah, let's do this. This would be the equation that kind of models the velocity of a falling object. Well, let's say I want to figure out, well, how far did it fall, right? How far did it fall? Now, you're probably familiar, right, just in terms of rates in general, that the displacement of an object, or I guess displacement, that's a kinematics term, just in general, the distance, right? The distance of an object that it's traveled is going to equal velocity times time, right? So hopefully that's pretty intuitive. If you're going 12 meters per second, after 3 seconds, you will have traveled 36 meters. Pretty intuitive idea, because it's 12 meters every second, so you just multiply by time. This only works, though, if you're moving at a constant velocity. And the only time, right, for something like a falling apple, no, it's not moving at a constant velocity. It's moving at a changing velocity. But, if you think about, the idea of very, very, very tall, small time intervals, and in really, really small time intervals, the object's motion is essentially constant velocity, right? The velocity doesn't change that much. So, we can you can kind of say that, well, dx, right, a small change in displacement for a falling object will equal velocity multiplied by that small change in time. Because in that very, 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 very small change in time, the object's velocity is roughly constant. And obviously, once you start minimizing these to zero and stuff, you're getting into calculus, and you can find the total displacement, right? I can integrate. And I can say that, well, the total displacement will equal an integral. And this integral will be from time 1 to time 2. Or you could even think of it as t initial, right? T initial minus t final. And if you're really, dealing with time, when you usually start the clock at 0, so we can actually just put in 0 right here. So it's going to equal our v as a function of time. Well, hey, we have that. It's v initial minus gt dt. And if you integrate this as a pretty simple integral, it's just v initial times time minus 1/2 gt squared. So this is one of the first kinematics equations that you have. It's change in x is going to equal the integral from 0 to t of v dt. And for constant right, for constant acceleration, this will actually equal 1/2 at squared plus plus v naught times time. And the key idea is that, yeah, this only really works for constant acceleration. Maybe on the AP test, they'll say like, hey, in this strange planet, the velocity at any time, right? So let's say an example. So if velocity is like 1/3 t to the 4th minus like 2 over t or something super goofy, right? Well, you can still find the displacement, right? You're just gonna have to, instead of using this equation, you have to take the integral. So, and I'm making this problem just off the top of my head, but you would say like change in x equals integral 0 to t. So you have 1/3, or I guess you can't really do 0 because as you get closer and closer to 0, right, you're getting infinite velocity. So, we'll just say, maybe we can do it from 2 to 4, right? From 2 seconds to 4 seconds. From 2 seconds to 4 seconds equals 1/3 t to the 4th minus 2 over t dt. You can integrate that, right? So if I think about how to integrate this, I would use a power rule here. So you would pull out the 1/3. It would be 1 to the 5th, t to the 5th. So that would be 1/15 times t to the 5th. If you're unsure about how I integrated that, I just took the 1/3 out. That's kind of like a constant, and then I do my reverse power rule, right? So subtract by 1, that sort of thing, and then multiply with the inverse. Hopefully you know that basic integration. It's on the equation sheet if you need it. Minus, and then the integral of 2 over t, that would be 2 times the natural log t from 4 to 2, and then I could just plug in whatever I need. So that's that's how you find like displacement if you're given a velocity function. If you want to find acceleration, it's going to be the derivative, right? So the derivative, you would just take the derivative to find acceleration. So acceleration is always going to equal dv dt, which is going to equal a constant for const acceleration, right? So for constant acceleration, it's a constant. So I can differentiate this. It would be 4/3 t cubed plus 2 over t squared if you were to differentiate, which is generally kind of easier. That is kind of the idea of kinematics. This is all math stuff, but calculus and graphs, it's like peanut butter and jelly. You can do the same thing with your graphs. So if they give you a graph like so if you have a velocity versus time graph, and I can just make like a fun little graph here, why not? You can find out information about this object's motion, right, using the graph. So I know that, well, at t equals 0, the object starts at rest, and because the v is 0, and then at b, it's gone to a positive velocity. So I know its velocity has increased. So it's kind of like increased this way. Or it's kind of, I should say it started moving this way, right? If we consider right to be positive, and then it stays at that constant velocity. Then it slows down, speeds up in the other direction, and then it begins to slow back down. So if I were to draw like a position versus time graph, right? If I were to do like my position versus time graph, I know that from A to B, it would kind of be constantly accelerating, which would look like a parabola based off this equation. And then from B to C, it'll be constant velocity. From C to this point, it's really going to slow down and then start going the other direction, right? Because it's going more negative. And then I can say from D to 0, it comes back to rest. So really, right, if you think about the derivative in this context, like the slope is the velocity. The derivative is a velocity. So you can see if I imagine my tangent line is increasing because my velocity is increasing. Right here, my tangent line stays the same. Velocity stays the same. And then tangent line kind of slows, or kind of gets less steep, and then gets more and more steep in the other direction, and then gets less steep. Everything is connected like that. And I can even do my acceleration versus time graph. So for acceleration versus time, it would kind of look something like this. There's a positive slope here, because I know the slope of velocity is acceleration. And I forgot to even mention, because I took this antiderivative, I'm so silly, that v is also equal to dx dt, which I kind of hinted at. Sorry for not making that clear earlier. But from a to b, right, constant acceleration. From b to z, zero acceleration. And there's negative acceleration. And there's positive acceleration again. So I can use the graphs to figure out the motion. Let's quickly do an example problem. And I guess before I do my example problem, let me derive one more kinematics equation using kind of the definitions. So I guess I can make kind of like a definitions box. So I could say definitions, and definitions as in like how these quantities are defined. Definitions. So I could say change in x is going to equal the integral of velocity times, or dt, right? Velocity is just dx dt. Acceleration is dv dt, and therefore velocity is also the integral of acceleration dt, right? So these are the very basic general definitions that can apply for any kind of motion, right? Whether you have constant acceleration, constant jerk, which is your the rate the acceleration changes, and there's also like constant snap. I don't know. There's like you can use any kind of motion with these equations. It all works just by definition of like how these are defined. So one last equation I want to derive is this equation. So I know change in x equals integral v dt from 0 to a time t. And what I also know is that acceleration is going to equal dv over dt. So what I can actually do is I could actually plug, or I can kind of rearrange this, and I get dt is going to equal, and actually you're going to see why in a second. I'll change this to like t1, t2. You'll see why in a second. But I can do dt equals dv over a, and then I get change in x is going to equal integral v times dv over a. And because I'm integrating with respect to v, my bounds change. And I would just, if you think about calculus class, you plug your t's into the function for v. So that would just give you like v1 to v2, so that our bounds are consistent with what we're integrating with. And we can, this a is a constant. So if constant acceleration, then what I can do is I can just like this a is a constant, which I could pull out and multiply to the other side. So I get a times change in x is going to equal integral v1 v2 v dv. And then to take this integral, it's a pretty simple one. It's a times change in x equals 1/2 v squared from, we can do v initial to v final really. And you can see we can multiply the two, and you get 2 times a change in x is going to equal v final squared minus v initial squared. So that's pretty nice, right? Now, this is one of the kinematics equations. Let's do a couple example problems. I've been explaining a lot. Let's just talk about where we would use each of these equations, like a couple examples. So let's say, we have, let's do, I guess, problem 1, right? So problem 1, we have a person standing here, and she is, let's say, a hockey player, and she's just standing there chilling, right? And she has her little hockey puck. Let's say that after like a certain, let's say at a certain instant, someone takes her hockey puck away. So there's this guy, he has the hockey puck, and he's moving at a speed 12 meters per second, right? So let's say after 3 seconds, she kind of realizes this, and she's like, oh, I gotta shoot. So I have to chase her. Why did I say shoot? I don't know. She has to chase her. So after 3 seconds, she's going to chase him with a constant acceleration of 4 meters per second squared, right? And within that 3 seconds, he would have, hopefully you understand that in those 3 seconds, he would have traveled further. So and let's say the question asks, how long will it take for her to catch him, if at all, right? So let's think about this, right? If you're going to approach this kind of problem, I know that let's say let's do this. So the position of this person, let's do this. The position of the hockey, the opponent, right? The position at any point will equal, let's do our constant velocity equation, right? Velocity times time. And if you forget really the simple equation, just remember, right? This is the same as, our 1/2 at squared plus v initial times time. And if our acceleration is 0, that term goes away. So I can just erase that out. Now I have my velocity times time equation plus the x initial. This is important, right? It starts at a certain x or after the 3 seconds, he's already gone a certain x position, and right? He's already traveled a certain distance, and that will be the initial position for when she starts chasing him. So I can even kind of show it like this. This is x initial, which x initial, that's just velocity times time, right? If you waited 3 seconds after he was initially there, and then this picture's a little misleading. It's more like she catches him right here, and then after 3 seconds he gets to this point, then it's just going to be 12 meters per second times 3, or 36 meters, right? So the position of the girl is going to be 1/2 at squared plus v naught times time plus x initial. And these are all 0 for her, right? Because she starts at rest, and she starts at where we can consider x to be 0, right? We could say like x is 0 right here. So I know at a certain time, they're going to be at the same position. Their x values are the same. So I can set them equal. 1/2 at squared plus is going to equal v naught times time plus x initial. So let's plug in some numbers. She's accelerating 4 meters per second squared, so 1/2 times 4, that's going to be 2t squared, is going to equal v initial for the opponent is 12, so 12t plus 36 meters. And this is just a quadratic equation that we can solve, right? Whether it be with our graphing calculator, which we are provided on the exam, or you can use a quadratic equation. Just for time's sake, I'm not really going to go into that, but you should find that there's 2 t values, right? Negative 2.2, I think, and then 8.2. The negative might be wrong, but we're not worried about negative time, right? We're worried about positive time. So that would be our answer right here, 8.2. So that's just how you use, right, your constant acceleration equations. If you think about the second problem we have, right, is we have a drag racer. So if we think about, we have a car, this nice Lamborghini or something. This drag racer is going to, and you use Lamborghinis for drag racing, right? So this car is going to accelerate. It's going to accelerate. How is it going to accelerate? It's going to, let's say it accelerates. I wrote this down somewhere in my notes. 17 meters per second squared for about 402 meters. So 402 meters. And then he's going to slam on the brakes. So after the 402 meters, right? He's going to slam on the brakes, and he's going to skid, let's say he's going to, after, let's say, what did I write down? 350 meters per second squared, right? Let's say he decelerates a certain amount, like let's say he decelerates 6.1 meters per second squared, right? So it's in the opposite direction. So even though he's moving this way, the acceleration in the opposite direction, we want to figure out what's his speed after this distance, right? Is he at rest? Is he still moving forward? Is he going backwards maybe, right? Maybe the brakes start accelerating them the other way. Like what's his speed at that point? So here's how we would approach that. We're looking at, well, let's start in this scenario. We know that we're solving for v squared, or v final. So we can use our v final squared equals v initial squared plus 2 times acceleration times change in x. Why am I using this equation? How did I know to use this equation? Well, I'm not given anything about time, right? So out of my equations that are provided on the equation sheet, I don't want the one with time. I don't know anything about time, right? What I do want to know is, I want to know, and you could, right? You could solve for time, but the approach that I thought of is using this equation, right? The main thing is, once I start plugging in my numbers, right, v final squared is going to equal negative 2 times 6.1 times 350 plus v initial squared. I just don't know v initial squared. Well, hey, I know that the v initial squared here, right? So if this is v initial squared, or yeah, well, it's moving at a speed v initial here, then I know, well, the v initial here is just the v initial at the end of the 402 meters, right? And if the drawing hadn't made it clear, this is like one linear problem. So he like speeds up for 402 meters, and then he starts slamming the brake, and then the distance here is a 350. I wrote meters per second squared. It's a 350 meters. So in this case, I can solve for the v initial right here, which is really the v final for the first stretch of the trace here. I can say, well, I'll say this is v1, right? Why did I write 40? I'm so lost. I don't know what I'm doing. This is the v initial, the same v initial, right? But this is just, we can just call this v1, so we're not confusing ourselves, because the v initial in this first scenario is 0. It starts at rest. So 0 plus 2 times 17 times 402 meters. Now, what I can do is I could solve for v1, and I could square root it. But I know this v1 is the same as this right here. So I can actually just take this whole thing and plug it back into here. So I can say v final squared is equal to 2 times 17, 402 minus 2 times 6.1 times 350. Take the square root, and I would get an answer. I think, what did I get? I don't know what I got as an answer. I kind of forgot. But I think it was, I think it was 93-ish meters per second, something like that. So these are just some constant acceleration problems, the type of problems you might see on the AP test, just using the equations, right? And knowing how to set them up, where to use them. So now let's talk about projectiles. We're not done yet. We got to talk about 2D motion. So we looked at one-dimensional motion, right? How do objects move in one dimension? Let's talk about 2D motion. So 2D motion is stuff like projectiles, right? If I kick a soccer ball, so if I'm right here and I kick a soccer ball, what I know is that, well, it's gonna move in 2 ways. It's gonna move up, right? Or I guess its initial velocity is going to be up, and then it's going to have an initial, or sorry, what am I saying? The initial velocity is going to have a component of it that's upwards, and it's going to have another component of it that's in the, horizontal direction, right? And from there, I could figure out, and this is not, and just understand, this is not the person kicking it up and then left to the same right. No. The initial velocity vector, like that vector, points diagonally, right? It just points, like that's the direction he kicked it. We can split it up into its components, and if you think about this angle theta, right, this is going to equal v cosine theta, where this is a v initial, and v initial in the y direction, that's v sine theta. And the main idea with 2D motion is that it's separate but independent, right? So, or no, that's not the saying. It's wait, what did my teacher say? It's independent but together, right? So it's the motions are really independent, but the so like the v in the x direction motion, I can just set up my own equations for that, right? I could say change in x is equal to change in x is equal to 1/2 a in the x direction t squared plus v initial in the x direction times time, and then I could say my change in y, right? It's y direction motion is governed by 1/2 a y t squared plus v naught y times time. So it's independent equations, right? These equations don't really depend on one another, but they're connected by the time, right? So however long it spends traveling in the y direction, that same amount of time is however long it's going to spend in the x direction. Does that kind of make sense, right? Like they're linked by time. They move together through time. So if it takes, I don't know, let's say 12 seconds to travel 40 meters, well, it's also going to take 12 seconds to go up and then back down again, because that's how the motion is linked. They start together and they end together. Hopefully that kind of makes sense. What I'm going to do real quick is just kind of show you how you can derive the range equation. Projectile problems are really similar to just your constant acceleration problems. So let's say I want to derive an equation for range, then what I can start with is I can start with my change in x equation, and in the x direction there is actually no acceleration. There's only acceleration in the y direction, and when we look at dynamics, it tells us why, because there's no forces in the x direction. We'll talk about that more, but the main idea is that change in x is just going to equal v initial in the x direction times time, and change in x, so change in x is going to equal, so v initial x, that's just v cosine theta, times time. So time I don't really know. I can use my y direction motion to figure out what the time in the air is. So for y direction motion, there for sure is acceleration. So change in y is going to equal negative 1/2 g times t squared plus v naught y times time. So if I think about this some more, or if I just kind of, so let's do this. After the time t, if this is like a symmetric launch where the ball ends the same height where it started, so for example, kicking something off the ground, then what I can do is I can just say, well, hey, the change in y, so what I could do is say the change in y is 0, right? It starts at the same height that it ends. There's no change in the final height after the time t. So I could then replace, right, v naught y with v sine theta times time minus 1/2 g t squared. I can divide one of the times out, right, because one of the solutions is when the t is 0, right? That's for sure when the change in y is 0. So I'm not looking for that. I'm looking for the other solution. I can get rid of that one of those t's, and then I can solve for t, right? I get 1/2 gt equals v sine theta, and I get t is going to equal 2 v sine theta over g. And then I can take this equation for time and multiply it right here. So 2v sine theta over g. And this is actually a pretty famous equation. You have 2 times sine times cosine theta. That's actually trig identity, which is equal to sine 2 theta. And then I get v times v, that's v squared over g. So this is a nice range equation to have in your back pocket if you can derive this in a pinch, or if you have it memorized, it can just help you out with some projectile problems and maybe get some fast answers out of it. Next, what I want to just look at is an example kind of scenario, or kind of like an example. I guess not really a problem, but just something to think about. Is, let's say we had 4 different projectiles, and we can make a little coordinate system like so, and let's say one of them was launched 60 degrees from the horizontal, and the others are launched at different angles, but they are launched with a certain velocity. This is kind of a weird way to say it, but they're launched with a certain velocity so that they all have the same height. So they're not launched with the same initial velocity, but they're launched with a velocity such that for their angle they reach the same height. So this is 45 degrees, and this is let's say this is 30 degrees, and let's say this is 20 degrees, right? They all have the same max height. And let's say a question asks, well, which one is going to spend the most, or let's start with this. Which one is going to have the largest largest component of the velocity directed up? Okay, that's a weird way to say it. Never mind. Which one just has the largest vertical velocity component, right? Which one, if you think about each of these vectors, which one will have the greatest one going up? Well, I don't know. If I want to prove this or figure it out, I don't know anything about time. So whatever equation I'm going to use, it better not have time. So I'm going to use my v squared equals v initial squared plus 2 times a times change in x. And let's take a look from when they start with their initial velocity and they go to the top, right? So the very top of their motion. Well, in this case, the v, at least in the y direction, because I'm really dealing with the y direction motion. So v initial y, 2 times a y times the height, right? The vertical height. At this point, vy is just 0, right? It's not moving. Well, it's moving. Whoa. It's definitely moving, but all of its velocity is directed in the in the x direction, right? So it's not moving vertically, so I can just see that, well, if this is negative 2 times gh, like that, I get 2gh is equal to v initial y squared. What this tells me is that the initial vertical velocity is not dependent on its angle, or it's not dependent on how its range or anything. It's just dependent on whatever the gravitational acceleration is and the height. And because they all have the max height, I know that this is same for all, right? Same for all. And therefore I can deduce, well, if you think about change in y equals change in y equals v initial times y times time minus 1/2 gt squared, then I know that, well, for their change in y after the total time t, it's going to be 0 because they start and end at the same height. And I can really solve for, I can see that, one of the t's go away because as I talked in the last example, one of the solutions is when t is equal to 0 for this quadratic equation. But 1/2 gt squared, I get 1/2 gt squared is equal to v initial y, and then, or in other words, t squared is going to equal 2, that makes more sense, 1/2 gt 2 v initial y over g. And we already kind of proved that Vy is constant for both, so the t is constant for both, which is kind of crazy, right? The time in the air is the same for all of them. So that would mean that for the 20 degrees one, it would have the biggest velocity in the x direction because it's traveling the most distance in the same amount of time. That means this ball kicked 20 degrees got kicked with the most like speed, right? Like it's moving the fastest at these points right here, which is, but it still moves at the same, or it still has the same time in the air. So that shows that the x direction motion is separate from the y direction motion. They're independent. Or I guess not separate. They move together, but they're independent from one another. The x direction motion has no effect on the y direction motion. If the y direction conditions are the same, meaning they go to the same max height, then they will have the same time in the air and the same v initial. So time in the air actually kind of depends on the y direction motion. If I drop a bullet versus shoot a gun at the same height, the x direction, the fact that the bullet is moving as a bomber, right? And that a bomber problem is when there's no initial y direction. So then in your equations, you just set this to 0. But even though I shoot the gun versus dropping the bullet, they would hit the ground at the same time. So that's a pretty crazy idea. And it's kind of the core projectile problem. So I'm just gonna quickly check how long I've been making this video for. Oh yikes, 36 minutes. Should I talk about relativity? I don't even know if relative motion is on the AP test, to be honest. I saw it. Actually, I can't really talk about the AP Physics 1 test I took. But yeah, let's cover it, right? I guess, the main idea of relative motion is that if I'm, should I do it or should I just save it for my dynamics? How about this? I'll save it for my dynamics video, right? So if you're really itching to learn more about relative problems, you can watch a separate video. Otherwise, my dynamics video, that's gonna be a long one. In my dynamics video, I'm gonna talk about relative motion. But this is a quick little video on kinematics, or not quick, but this is a video on kinematics for the AP Physics C test. Thank you for watching. Have fun studying. The test is in I don't even know, to be honest. I think it's a month and a half at this point. But yeah, thank you for watching.